Yeah, well, welcome. It's a great pleasure to start the day off with the first speaker, who is Valentin Blomer from Bonn. He's one of the world-leading experts on what I like to call the analytic theory of automorphic forms, or what used to be called modular forms. He's won many, many awards, including ones for being a concert pianist. So he's a multi-talented guy. Maybe you can get him to play later if you're lucky. The analytic theory of modular forms, or automorphic forms as I'm calling it, saw great advances in GL1, one-by-one matrices in the 60s and 70s. And in the 80s and 90s, there was tremendous advance in connection with two-by-two matrices. And most of us can deal with two-by-two matrices. When it comes to bigger matrices, it's a little hard to multiply. But can you imagine linear algebra where you're restricted to 1 and 2 dimensions only? It wouldn't be much of a subject. And similarly here, in my view, the subject is not going to be advanced to the point where we are able to solve the real big problems until we understand n-by-n matrices and other groups. And that is a topic that has been investigated since the beginning of the century, but the progress is very slow. It's very difficult. The analytic theory is very difficult. But there has been progress over the years, and especially recently, and this workshop that we have here is highlighting some of these advances. And leading the way in these advances is Valentin Blomer. So it's a pleasure to introduce him. And the title of his talk is Density Theorems and Applications.
All right. Thank you very much, Peter, for the introduction, and thanks very much for the invitation to speak here. Yeah, Density Theorems and Applications is the title, and maybe I should start by explaining what a density theorem is. In very simple terms, it's a very sophisticated bound on the cardinality of the empty set. There is more to this. It's more subtle than that, as we'll see, but maybe as a first-order approximation. Okay, so let's start with something that is probably familiar to most of the people in the audience, the Riemann zeta function. And well, we are interested in the zeros of the Riemann zeta function. And let's count zeros beta plus I gamma of height at most t that are to the left of sigma. So here is a picture. The Dirichlet series is absolutely convergent to the right of 1. The functional equation translates this to the left of 0, and the zeros should be lined up on the half line. And because there is an Euler product, there are no zeros to the right of 1. And it's a classical fact using some complex analysis and the functional equation that in total we have about t log t zeros of height at most t. And well, the Riemann hypothesis says that there are no zeros to the right of 1/2. N of sigma t is 0. Now, the Riemann hypothesis is, as far as I know, out of reach, and we're not able to prove this at the moment. So you might want to look for substitutes. And this is what a density hypothesis is like. It's a linear interpolation between the region where we trivially have no zeros and where we know all the zeros. And so the density hypothesis would be a count for the zeros to the right of sigma of this form, where ideally c is 2. So this means if sigma is 1, we get an exponent 0. If sigma is 1/2, we get an exponent 1 with an extra epsilon that maybe accounts for this log. That would be a density hypothesis. So this is, again, for sigma bigger than 1/2, probably a bound for the empty set, but a very good bound for the empty set. And we don't know this yet, so c equals 2 is not available. The record is 50 years old. It's a little worse than 2. But nevertheless, the idea is this bound is useful because, OK, there may be a few zeros off the critical line, but the further that they are away, the fewer they are. In other words, big violations to the Riemann hypothesis happen very rarely. Yeah? OK, why do we care? Why is this an interesting problem to consider? Well, when we are interested in the Riemann zeta function, we are interested in primes. And it turns out that the density hypothesis in many applications is as good as the Riemann hypothesis when we are interested in the distribution of primes. So it's really a very strong substitute for the Riemann hypothesis. And here are some examples. So suppose we want to count primes up to x. We usually count them with a logarithmic weight in order to get a nice asymptotic. And let's suppose you want finer distribution, let's say in a short window. So let's suppose we want a short interval count from x to x plus h. And the density hypothesis with an exponent c allows us to take a window of size 1 minus 1 over c. Yeah? In particular, if c equals 2, that would be the perfect density hypothesis. We get 1 minus 1/2 is 1/2. So we get a square root size window, which is as good as the Riemann hypothesis can give us. Yeah? So the density hypothesis in this application is as good as the Riemann hypothesis. A variation of this would be not for the Riemann zeta function, but for more general Dirichlet series. And then you get the Bombieri-Vinogradov theorem, a very famous theorem that basically tells us in somehow to first order approximation that in almost all long arithmetic progressions, primes are equidistributed. And this is a very similar kind of theorem. A short interval zooms in some way, and an arithmetic progression also zooms in a p-adic way. Yeah? So these density theorems can be very useful because they tell us something about the finer distribution properties of primes. OK, I want to move now to the automorphic world and apply the same concept in the automorphic world. So let's start with a relatively basic example. We take the upper half plane modulo a congruent subgroup. So the upper half plane is well known, and a congruent subgroup is a finite index subgroup of SL2Z that contains some principal congruent subgroup gamma of Q, which is this kernel. Yeah, so this is a typical hyperbolic surface. And we are interested in the L2 space of this hyperbolic surface. And this allows a spectral decomposition in terms of what we call cusp forms. This is a discrete set of spectral components. And Eisenstein series, which is a continuous set of spectral components, and the constant function. And there's in particular the Laplace operator, but there are more operators. I don't want to go into this. But there are many operators acting on this space, L2 H mod gamma. That's why it's a very interesting space. It's a very rich space that's acted on by many operators. OK, so these functions are all eigenfunctions of the Laplacian. And you can write down oh my, something is hopping here, whatever. You can write down the eigenvalue equation. And somewhat artificially, I'm going to write the eigenvalue as 1/4 minus mu squared. And a famous conjecture says that these mu's should all be purely imaginary, which means that mu squared is a negative number. That means minus mu squared is a positive number or a non-negative number. So this means the eigenvalue is at least 1/4. Yeah, 1/4 or bigger. This is the famous Selberg or Ramanujan conjecture, and unfortunately, it's totally out of reach, at least in this amount of generality. And you can view it like the Riemann hypothesis for automorphic forms. Somehow the eigenvalues are lined up on a certain line, just as the zeros of the Riemann zeta function should be lined up on a certain line. And again, you can measure the failure by measuring how far away such a mu is from the imaginary axis. Okay, so let's do this. Let's count eigenforms such that the real part is bigger than some given quantity sigma. Okay, and again, we can bound this rather simply by just by the volume of the group. But we can also remember that the Laplace operator is a positive operator. And so the eigenvalue is certainly at least 0, which means that after 1/2, there cannot be any eigenvalue. So we have no such forms where sigma is bigger than 1/2. And okay, we can now again linearly interpolate between these two fairly simple bounds. And this is Sarnak's density hypothesis, first announced at his ICM talk in 1990, so it's more than 30 years old. And it's a linear interpolation between these two trivial bounds. Again, probably a bound on the empty set, but anyway. All right, why do we care? Why would such a density result be useful? I'll give you a couple of applications. And the first application is what Peter Sarnak calls optimal lifting. And you remember that there is a surjective map from SL2Z to SL2Z mod QZ. And since it's surjective, we can look at pre-images. And so take a pre-image, and among all the pre-images, what's the smallest one? Yeah? So in other words, for a given gamma, I look at all the pre-images, and then I take the smallest one in terms of some given norm, take your favorite norm, and I normalize this by the size of the group SL2Z mod QZ, which has size roughly Q squared. I can do this for every gamma, and then I can look at the worst case scenario. I take the maximum over all gammas, or I can take the average, the expected value over all gammas. Okay? And then it's a simple argument using the pigeonhole principle that you cannot do better than one. I mean, these elements have to have pre-images, and just by the pigeonhole principle, a trivial lower bound is 1. And then the lim inf is trivially bounded by the lim sup. And it turns out that the lim sup is 4/3. And to get an upper bound for the lim sup, you can use a greedy algorithm. Just pick every coordinate at a time and make it as small as possible. But it turns out that this greedy algorithm is sharp, and you can actually construct examples where the smallest lift is not quite as small as you would expect, namely 1, but slightly larger. Okay? Okay, well, that's the state of the art as far as elementary approaches are concerned. But it turns out that when you have a density hypothesis available, then on average, the smallest lift is 1. In other words, typically, the smallest lift is as small as you would expect. Again, there are some counterexamples, but typically, the smallest lift is as small as you would expect. Yeah? And that's what a density hypothesis can give you. Second application, maybe even more down to earth, just simply count matrices in SL2Z, well, not in SL2Z, but in some principal congruent subgroup of height up to T. Okay? And as long as you keep the congruent subgroup fixed, it's not hard to see that this is something like T squared over the volume. But what happens if you want to make this uniform? If you allow not only the height to grow, but also the congruent subgroup to grow? I mean, if V is very big, if the volume is very big, then this can't be true. I mean, if the volume is, let's say, bigger than T squared, this just simply must be wrong. And what would be a uniform count? Now, well, in Dreamland, the error term is always the square root of the main term. So that is what you might want to dream about. But this is probably not even true. I don't know whether it's true, but it's certainly totally out of reach to be provable. So a more realistic conjecture would be to just take the square root in the numerator, but drop the square root in the denominator, and use this sort of upper bound. So T is kind of the correction term if V is too big. That would be a realistic conjecture, and something that, if you're familiar with bounds for primes in arithmetic progressions, the Riemann zeta function would, like the Riemann hypothesis for the Riemann zeta function, would give you analogous bounds in such context. So this could be a realistic setup. And it turns out that all these three statements are with a grain of salt equivalent. If you have a density hypothesis, you can prove optimal lifting and uniform counting, and each implies the other. Not exactly, but with a grain of salt. Morally, they are equivalent. And that's what Peter Sarnak and Schuhe proved in 1995. They proved all three statements And it turns out that they are more or less equivalent. Third application, just very briefly, take just a local representation on SL2R. So there's, for now, there's nothing global, just a representation of SL2R. And now we ask how many global automorphic forms do we have whose local component is this given pi, has the Laplacian eigenvalue 1/4 minus mu. Yeah? How often do you get a global guy that matches this local one? And if we call this number, this multiplicity of pi, m pi gamma q, then the density hypothesis implies this upper bound. And somehow the question is, you look at higher and higher congruence covers. You have your basic surface, and then you look at the tower of congruence covers, and then you ask how often, like how does the multiplicity change with the cover? That's why you call it limit multiplicities. Okay, so I hope I advertised the density theorems enough to convince you that this is really a useful statement and a useful thing to have, and a very good substitute for very big conjectures. Okay, let me now turn to the more general setup. So Peter announced this already, that we want to go to higher rank. So let's see what happens in higher rank. We take now representations on PGL-N rather than PGL-2, and see what happens. So we take a place. That's our testing place. If you want, you can imagine that this is infinity, the Archimedean place, or let's say some fixed prime, your favorite prime, 5. And my representation at each place comes with an n-tuple of Langlands parameters, and because we are in PGLN, they sum up to 0, so it's really just n minus 1 independent parameters. So if n is 2, there is just one independent parameter, and this was the mu that we had earlier. Okay, now it's an n minus 1 tuple, and I want to know how far is this n tuple away from being purely imaginary. Yeah? So I check the real part, and I take somehow the worst case. I take the maximum over all the real parts, and if the n tuple or n minus 1 tuple is purely imaginary, then this would be 0. And so the representation is tempered at V if and only if this quantity is 0. Then all the components are purely imaginary. Okay, and now again I take my favorite family of automorphic forms, a finite family, and I count how many bad guys do I have. For a given sigma, how many pi's violate or have real parts that are more to the right than sigma. Yeah? And so what's the worst case scenario that can happen? This would be the trivial representation. Their sigma is 1/2 times n minus 1, which is very much a real number and very much not an imaginary number. So this would kind of the largest distance from the imaginary axis. And then I also have the trivial bound, simply the whole family. The whole family is always a trivial bound for the size. And so a natural generalization of the density hypothesis to PGLN is a linear interpolation between these two trivial bounds. If sigma is 1/2 times n minus 1, I get an exponent 0. And if sigma is 0, I get an exponent 1. So that's just the linear interpolation between these two trivial bounds. Now, higher rank is different from rank 1. And there are a few maybe unexpected phenomena that one should be aware of before one tries to prove this. So first of all, for PGL2, this is known for all reasonable families. If you pick your favorite family that comes up in practice, then such a density result is available. And by many people. So this is kind of classical. Higher rank has been completely open. And as I said, there are some unexpected phenomena. So first of all, if you restrict to a cuspidal family, then we have very good individual bounds. The sigma can never be larger than 1/2, which in view of 1/2 times n minus 1 is very small. So there is a huge gap between trivial and cuspidal. However, the moment, and you can even improve this. You can do a little better than 1/2. The moment you leave cuspidal representations and also allow non-cuspidal representations, you do find all sorts of nonsense, all sorts of representations whose sigma is very much non-zero. Yeah. And even worse, but there are not so many. So this does not necessarily violate the density hypothesis, but it violates Ramanujan. Even worse, the moment you pass to other groups other than PGLN, there are even cuspidal representations where sigma is large. But again, not so many. Yeah? So what I'm saying is that obeying Ramanujan is a fragile property. And there are all sorts of representations that violate Ramanujan. However, there are not so many. Yeah? And so a density theorem still has a chance of being true because there are maybe not so many. Yeah? Here's a small picture. Let's say for n equals 7, then you have the trivial representation sitting here at 3. This blue line would be the density hypothesis. You have the Eisenstein series sitting here at 1/2, 1, 1.5, 2, and 2.5. So there are contributions, non-cuspidal contributions at these points. And this line here is somehow the Luo-Rudnick-Sarnak bound for cusp forms. So the density hypothesis for a cuspidal family is only interesting in this region here, because from that point onwards, it's 0 anyway. Yeah, but in this region, a density hypothesis, even in the cuspidal case, is very useful. Okay, so to summarize, the density hypothesis is rather robust. It can also take into account some non-tempered representations. It's more accessible than proving Ramanujan, because Ramanujan is probably out of reach, but we'll see that the density hypothesis, at least in certain cases, is not. And it's often useful in applications. So it's really something that we need in applications. So I hope I can convince you that this is a very useful thing to have. Okay, now having advertised density theorems, let me talk a little bit about proofs and about methods, maybe not full proofs and not even sketches of proofs, but at least what are the ingredients? How can you attack such a problem, and how can you attack density theorems? Okay, how can you count representations that are not tempered? Okay, let's look at the setup. My group is PGLN in Iwasawa decomposition. I take a congruent subgroup. I look at the locally symmetric space, G mod K mod gamma, and I fix a test function that's by K invariant. It lives on G, and it's by K invariant. Okay, and with this test function, I can construct what is called an automorphic kernel. I sum my test function K over matrices gamma, and this function, as a function of x and y, is in both variables right K invariant, because little k is by K invariant. It's in both variables left gamma invariant, because that's eaten up by the summation of gamma. Yeah? So this is well defined. It's well defined as a function on x times x. Okay? And as we have seen, this L2 space of x has a spectral decomposition. Orthonormal basis is a bit sloppy. There is also a continuous part, but let's not worry about this. We can spectrally expand this function and get a different form of this function as a sum over the spectrum and eigenfunctions, and it contains a weight function h that's an integral transform of k. There is a recipe how to go from k to h, and h as an argument has the Langlands parameters. Yeah? And so you have an identity between these two boxed formulae. These two boxed formulae are the same. and this is an identity. And whenever you have an identity, you can do something with it. This identity is called the pre-trace formula. And you can do several things. For instance, you could compute the trace by integrating over the diagonal, maybe in a regularized way. Either integrate this expression or that expression. This is the Selberg trace formula. Or you can do some other integration. You can include unipotent periods. You can integrate over n in both variables against some character. This is called a relative. This looks a bit random now, but it turns out that this is a very useful setup. This is called a relative trace formula because there is somehow it's relative to these unipotent periods here. And you can do this also in two ways. You can either integrate this expression or that expression in this way. There are many other things you can do. You can integrate over whatever you want, but it turns out that these two ways have been proved to be very useful in practice. Either way, you end up with an expression that has what we call a spectral side and a geometric side. It has a sum over the spectrum with some function that sees the Langlands parameters and certain weights. And on the other side, you have a sum over matrices with certain weights. And these matrices are grouped into quotients or conjugacy classes depending on what you do. So that's somehow the general shape of a trace formula or a spectral summation formula that you use in practice. OK, what do you do with this? Well, first of all, you want to pick out your family that you're interested in. So you design these weights in a way that they resemble the characteristic function of your family. Okay? Next, you want to identify those where the Langlands parameter is very much non-real and where the sigma is big. So you design this weight h in a way that it puts a penalty on those where sigma pi is large. So they get highlighted. They get a big contribution, whereas everything else gets a small contribution. Okay? And once you have designed the spectral side, you bound the weights that appear on the other side, which of course depends on all the choices that you made on the spectral side. You try to bound this as best as you can. Yeah, so that's what you have to do. And in this way, since the left-hand side penalizes large values of sigma, this has a chance of giving you a density theorem. Now, of course, this strategy is very abstract. If you want to do this in practice, this requires quite a bit of work. And depending on the setup, it requires work in very different areas, in analysis, representation theory, or algebra. And in this talk, I can't go into any details. But yeah, I want to give you at least one ingredient that comes up on the geometric side. And this is Kloosterman sums. You may have seen Kloosterman sums, or you may not have seen Kloosterman sums. Classical Kloosterman sums were kind of invented, or at least used, by Kloosterman in his thesis about 100 years ago. And these are exponential sums. So you sum over all primitive residue classes d mod c, sum exponential, and d bar are inverses to each other modulo c. OK, it's not clear why this is a useful object, but we'll see in a moment that it is a very useful object. It comes up in number theory very, very often. And if you like, you can write it in a slightly different way. You have two characters, and you sum them over x and y, satisfying the equation x times y equals 1. This is precisely this condition here. You can view this as let's say C is a prime. You can view this as an algebraic variety over Fp, given by the equation x times y equals 1. OK, whenever you see such an exponential sum, your first instinct is to get an upper bound for it. And the trivial upper bound is, well, just the number of terms, because each exponential is bounded by 1. Okay. So the trivial upper bound is C, or if you are careful, just the number of coprime numbers up to C. But there should be a lot of cancellation. I mean, at least if m and m prime are not just both 0 or something like this. I mean, these exponentials should not all point in the same direction. There should be lots of cancellation. And indeed, there is. And that's André Weyl's famous bound. He proved essentially square root cancellation. There is some fudge factor here, which you don't need to worry about. But there is essentially square root cancellation. So instead of the trivial bound C, you have the non-trivial bound square root of C. Yeah, and this has a very practical, somehow, interpretation. If you think of a random walk, if you view these exponentials as random numbers, and let's say they are all real for simplicity, so they could either be plus or minus 1, and so with probability 1/2 they are plus 1, and with probability 1/2 they are minus 1. And then you follow this random walk. With probability 1/2 you go right, with probability 1/2 you go left. Then after n steps you should be roughly at square root n. And this is precisely what is happening here. So this square root cancellation is very, very natural. It tells us that somehow these exponentials are kind of independent and behave like random numbers. Yeah, this bound for classical Kloosterman sums is one of the most useful bounds in number theory. Comes up everywhere. When you open a random paper in number theory, you'll have high probability that this bound is used somewhere. Okay, what does this look like in general? What is a general Kloosterman sum? And I'm saying this because these Kloosterman sums are precisely what comes up on the geometric side. Now, a general Kloosterman sum looks a bit frightening. So now everything are n-1 tuples instead of numbers. So these m and m prime are now n-1 tuples. C is an n-1 tuple. You take an element in the Weil group. N is the usual unipotent upper triangular matrices. And NW is a certain subset of these. And T is the diagonal torus. And you take a character on n, a character, this comes from the first superdiagonal, and looks like this. Oh, and I forgot this E is really e to the 2 pi I, but we analytic number theorists don't care about the 2 pi I, we just write E. So this is exp of 2 pi I of this. And C is an n-1 tuple from which I form a diagonal matrix. I call this C star. And the Kloosterman sum is the following thing. It comes from the Brugha decomposition. Here you see the Brugha decomposition for a given Weil element. And you sum on the left and the right over unipotent matrices NQ modulo NZ. This set is intersected with your group gamma, whatever that is, some congruent subgroup. And this is the set you're summing over, and then you're summing against these characters. This is a general Kloosterman sum. You can write it down in one line, but analyzing this is not so simple, but it's an easy exercise, a few lines of computation to see that for n equals 2 and the long Weil element, you just recover the classical Kloosterman sum that I had on the previous slide. So in this sense, it's a generalization, and it is what comes up in practice. Okay, now here again is this generalized Kloosterman sum. And unlike the classical case of SL2 Kloosterman sums, there are many, many open problems for such Kloosterman sums. And maybe the most basic, which is not an open problem, but the most basic problem is what's the trivial bound? I mean, it's not even obvious what the trivial bound is. Like, how many terms are in this sum? It's a finite sum, but how big is it? Yeah? How many double cosets do I have? This is totally non-trivial. This is known. This is a result from 1998, Dabrowski and Reeder, and they showed that the cardinality of this set is basically the product of the moduli. Yeah? But this is by no means easy. I mean, counting these double cosets is by no means easy. Okay, so this is the trivial bound. Okay, so your next obvious question is there cancellation? So this does not take into account that there is cancellation in the characters. This is just the cardinality of this sum. Yeah, what are non-trivial bounds? Do we even have square root cancellation? Is the true size the square root of the product of the moduli? That would be maybe the most optimistic conjecture. This is known in one case, or has been known in one case, namely for this Weil element, which has a 1 here and then the identity n-1 identity here. This is the so-called Coxeter Weil element. And for this Weil element, we have a bound 1 minus 1 over n, and this is sharp. So this tells you in particular, A, you need to use deep tools, namely Döhlin's bound for hyper-Kloosterman sums. And secondly, square root cancellation is generally wrong. Yeah? 1 minus 1 over n is typically not 1/2. It is 1/2 if n equals 2. But if n is not 2, then it's strictly worse. Yeah? Other questions that you might ask, when is this actually 0? Are there situations where there is complete cancellation? When is this 0? Also interesting, that would be useful. I mean, somehow your instinct is you want to use algebraic geometry to estimate these exponential sums. But in order to do this, you first have to have underlying algebraic varieties. And it's not at all clear how to write this set of double cosets in terms of algebraic varieties. For classical Kloosterman sums, it's just xy equals 1. But here it's not at all clear how to do this. Yeah? So even though you can write down these Kloosterman sums in one line, it's not clear how to analyze this. All right. Yeah, so here are some results. Okay, it's gone somehow. Anyway, so for the long Weil element, a former student of mine and myself, and independently Miao, we got non-trivial bounds for the first time, reducing the exponent 1 to 1 minus a bit, where this a bit is of size roughly 1 over n squared. I'm not sure if this is sharp or not. My gut feeling is that the correct order of magnitude should be 1 minus 1 over n. But yeah, so certainly there is some saving. There are some non-trivial bounds. We can also do this for another Weil element. This looks, again, completely random, but it turns out that this is a very, very useful Weil element that is somehow the most dominant one in many applications. It's the Weil element where you have a 1 and a 1 here, and then the identity matrix in the middle. And here we also get a saving that's of size 1 over n. And it turns out that this is actually sharp. If you look at moduli p, n minus 1 times, you can evaluate this on the nose. You can exactly evaluate this as p to the n minus 2. And you see the trivial bound would be p to the n minus 1. So the saving is really of order of magnitude 1 over n exponent. Yeah, so the bound is sharp. Yeah, so the upshot is it is possible to get non-trivial bounds, at least for some Weil elements, for these Kloosterman sums. And in some cases, even sharp bounds, but the sharp bounds are not square root cancellation. They are worse than that. All right, so this was kind of an interlude to show you some of the ingredients that are necessary if you deal with these trace formulae. There are many, many other ingredients that I'm not going to talk about today. But this is one that implies or involves some algebraic geometry and also some maybe arithmetic combinatorics. OK, so back to density theorems. If you combine all these ingredients, in the end, then what we try to prove is such a density theorem. So that is what we had on previous slides. Again, this is a linear interpolation between two trivial bounds. And here's the first result by myself a couple of years ago. So this now depends very much on the family that you're going to take. And my families are always such that the infinite parameter is bounded. So somehow the Laplacian eigenvalue, if you wish, is in a fixed box, but the congruence group is going to grow. And then you can take various congruence groups, and a very classical one is the Hecke congruence group that has zeros here in the bottom line, mod q. Okay? So this is a group of volume q, q to the n minus 1, roughly. And for this family, I proved this density theorem. For cusp forms, even with a better exponent, so this is somehow a stronger interpolation, instead of n minus 1 over 2, I get n minus 1 over 4. Of course, this is only possible for cuspidal representations, because we have seen it can't be true. There are non-cuspidal representations that are worse than that, but if you restrict to cuspidal representations, you can hope to prove something better. And yeah, this is roughly twice as good as the original density hypothesis in the cuspidal case for this Hecke congruence subgroup. All right, yeah, so that's one example. Second example, together with Edgar Assing, who is also here at this conference, we looked at the principal congruence subgroup, so gamma q, and again, bounded infinite parameter. And there we include all the representations, including non-cuspidal ones. We allow q to be square-free. Up here, q is prime. Here, q can be square-free. And we prove this density hypothesis as well. So let me say, maybe for the experts from a methodological point of view, the nice thing about the Kuznetsov formula is that the moment you include these unipotent periods, you kill everything that has no non-zero Fourier coefficients. And in this way, you kill, for instance, the trivial representations. You kill all sorts of residual Eisenstein series. This is very convenient. This gives you a chance to improve this n minus 1 over 2, because, I mean, somehow you need to remove the trivial representation. Otherwise, you will never be able to do better than n minus 1 over 2. But the Kuznetsov type formula has this already incorporated, because it's insensitive to the trivial representation. So then you have a chance to do better than that. The moment you want all representations, you have to artificially reinsert them again. So even for the second theorem, we use the Kuznetsov formula, but then artificially we reinsert everything else that's not seen by the Kuznetsov formula. All right, and one more. You can also take, another very interesting subgroup is the Borel subgroup. That's congruent 0 mod q for the upper triangular part, for the lower triangular part. And here again, q is prime. The infinite parameter is bounded. And it's a theorem that, in this case, also this density theorem holds. Removing the primality or square-freeness is more than a technical issue. It may be in the cards, but it's not so easy. So primality and square-freeness are used quite extensively. Also, we have nothing to say if we want the Archimedean parameter to grow. So right now, these are only, as we say, level families. Yeah, so the non-Archimedean aspect is allowed to grow, whereas the Archimedean aspect is not allowed to grow. OK, I'm sure you want to see applications. Why do we care? What can we do with these results? And I showed you already the applications for PGL2 and for PGLN. There are essentially the same applications, except that they are not quite so direct. There is more input required than just a density theorem. And it turns out that one major issue are Eisenstein series and their treatment. We'll see in our workshop, we'll see quite a few talks on this topic. I don't want to go into this here. But yeah, let me say that there is much more than just the density theorem. But the density theorem is one of the important ingredients. And together with some more work, Jana and Kamba solved the uniform counting conjecture. So for Q square free, you have this bound. That is somehow the natural generalization. So the first term is what you get simply from the volume count. So this is the volume of the region where you are counting, and this is the square root of the numerator. So somehow this is the best you can hope for with this technology, and this holds for general n, and general Q as long as it's square free. Similarly, the optimal lifting, again, Q square free. This is both based on the density theorem for the principal congruent subgroup. For almost all gamma, so for a typical gamma, there exists a lift that is as small as the pigeonhole principle tells you. If you pick your favorite, your typical gamma in this residue ring, then there is a lift that is as small as the pigeonhole principle. I have slightly changed the normalization. That's why this is now 1 plus 1 over n. And what does it mean for almost all? If you're interested in the fine print, here's the fine print. For all epsilon bigger than 0, there exists a delta bigger than 0 such that the number of gamma without a lift of that size is a delta less than the entire number of gammas. That's somehow the precise statement. Okay, this optimal lifting can take many forms depending on what group you take. Optimal lifting for the principal congruent subgroup looks like this. Optimal lifting for the Borel subgroup has this very charming form. So let's look at the set of all flags in, I guess this should be fq to the n. So you take, this should be fq. This should be sequences of vector spaces of growing dimensions. And this is acted on transitively by SLNZ. And now you can pick two flags and ask, so you know there exists a gamma that sends one to the other because there is a transitive action. But what's the smallest such gamma that sends you from x to y? And the smallest such gamma is at most of size q to the half, and that's, again, the best possible bound that the pigeonhole principle predicts. This doesn't hold everywhere, but it holds for almost all pairs. So somehow if you pick a typical pair xy, then you find a matrix that sends you from x to y, and that's as small as it can be. And so that is optimal lifting in this context. The optimal lifting somehow is sensitive to what group you have in mind. And that's what it looks like here. Okay, as an afterthought, if you're interested in, let's say, this uniform counting conjecture, and if you're a number theorist, you may say, okay, I mean, looks very elementary. Why can I not just count this with my fingers? I mean, why do I need all this high-level machinery to just count matrices? I mean, there must be a simpler way. And so suppose, once again, we want to count matrices in some congruent subgroup of height at most t. So let's look at the case n equals 2. And there it really can be done by bare hands. And okay, let's just do it. I mean, an element in gamma of q looks like this. It must be congruent to 1 modulo q. So it's of this form. The off-diagonal entries are multiples of q. The diagonal entries are 1 plus multiples of q. Okay, with a, b, c, d integers. Every entry is bounded by t. So that means a, b, c, d are bounded by t over q. Okay, and you have the determinant equation. You want that determinant is 1. You simply compute the determinant. Okay, everybody knows how to do this. And you order this by powers of q. That should be 1. Well, okay, you cancel 1 on both sides. The second term is divisible by q squared, so the first term must be divisible by q squared too. But you only see a factor of q, which means that a plus d must be divisible by q. So there is at least one relation. A and d cannot be random. A plus d must be divisible by q, which basically means you can fix a, but then d has an extra condition mod q. And once you fixed A and D, then by a divisor argument, also B and C are more or less fixed. Yeah? Every number theorist knows how to do this. And so in this way, you can easily get an upper bound for the number of matrices in gamma of Q of height T. And from this, you can get the density hypothesis. And from this, you can get optimal lifting. This is precisely, well, there is more to it. But this is somehow the idea that Sarnak and Schuhe used. And I mean, they did it in more generality. But at least there is a chance that for n equals 2, you can still do this more or less with bare hands, the counting problem. But this is misleading, because really the determinant in 2 by 2 matrices is AD minus BC. And the determinant for 3 by 3 matrices is not so simple. And yeah, this totally doesn't work in higher rank. So you can do this with bare hands for n equals 2, but in higher rank there's at least as far as I can see. So far, yeah. At least as far as I can see, right.
You can prove somebody can't do it.
Yes, yes, yeah. Yeah, I'm not saying it can't be done, but it's infinitely harder, at least, to use such an argument in higher rank. And so, yeah, so let's say seems very hard. I think that's safe. Yeah, so what do we do instead? We have this counting problem here, which we want to solve. We spectrally expand the counting problem using the pretrace formula. We don't know how to deal with the spectral expansion. We modify the weights a little bit to get a spectral expansion that looks like something that resembles the Kuznetsov formula, which for the experts means you include first Fourier coefficients like L1 adjoint pi and stuff like that, and you change things a little bit otherwise, and you need to make sure that this doesn't destroy somehow the asymptotics or the upper bounds. Then you apply a relative trace formula in the other direction and get a different counting problem, namely the counting problem of counting double cosets. This is something we are able to solve. And then looking at this whole sequence of terms or steps, we can solve the original counting problem. Yeah? But somehow the magic happens in going from here to here. These are both spectral expansions, but of somewhat different shape. And you need to make sure that not too much gets lost or destroyed in this way. But then you can apply a different trace formula in the other direction, get a different counting problem, and yeah, this is solvable in this way. So this is somehow the abstract framework of this counting problem. And again, if someone sees an elementary way, even better. All right, that's all I wanted to say. Thank you very much for your attention.